Hello, and welcome back to Shiksha DaCosta. Today we're going to learn about the graphs of quadratics that are in vertex form. So today we're going to learn both how to graph a quadratic relation in vertex form, which is y equals a times x minus h squared plus k. We call that that is a quadratic relationship. It's always going to create a parabola on a graph, and we're going to learn how to draw that parabola. We're also going to learn how to actually come up with an equation just like this one if we already have the graph. And if we do that, then hopefully we can move back and forth between them pretty quickly. This is your success criteria for the day, of course. By the end of this lesson, you should be able to sketch by hand a quadratic if it's given to you in vertex form. And you should also be able to determine the equation of a quadratic in vertex form, given a graph of a parabola. To start off, I'm going to ask you something that sort of presupposes your knowledge about transformations of a quadratic relationship. There's a point here, point A, and it's at these coordinates where x is 2 and y is 4. And that's a point on the very basic parabola y equals x squared. Now we're going to transform this parabola, and we're going to do so by changing the a value to -3, the h value to 4, and the k value to 10. Okay, so this is our new quadratic relationship. Its graph looks like a parabola, but it's been transformed in a whole lot of ways, so it's very different than the basic parabola y equals x squared. I want you to try to list all of the transformations on y equals x squared, which would have turned it into this graph, and then I want you to find out where is the new location of point A. We call that A prime. Where did that point end up moving to on this parabola? Pause the video here and see if you can do that. Okay, well, hopefully you realize that, well, in this parabola here, or in this equation, the a value is now -3. And when a is negative, that's always a reflection in the x-axis. And because a is -3, the absolute value is 3. That means that this parabola was vertically stretched by a factor of 3. That means all of the y coordinates got multiplied. That's why we use the word factor. They were multiplied by 3. The next one I'm going to look at is, of course, our h value. And our h value in this case is +4, not -4, although this says x minus 4. Remember that this is x minus h. So there was a translation, or this parabola was after it was stretched and reflected, it was shifted 4 units to the right, because that's +4, and that moves it right. And finally, the k value is 10, and that means that this parabola was moved 10 units straight up. And that's after these two things had taken place. Now, maybe I've answered my own question a little bit too early, but h affects the x value. It moves it left or right. But both a and k both affect the y value. So I want you to think about and answer this question. Which of these two do you think would make sense to do first? Because if you do them in the other order, you don't actually get the same graph. Pause the video here and see if you can discuss this with a friend, or if you can think about the answer to this question. Well, some good reasoning might lead you to believing that A comes before K because of bed mass. A is something that is being multiplied, whereas K is being added. And it's not specifically for that reason, but it kind of is. That, once we choose a value for X, -3 is multiplied by that before the 10 is added. And so A is applied, this vertical stretch and reflection is applied before the shift up or down that K does. So if we started with this point A, 2, 4, we know that the x values got increased by 4, because there was a translation 4 units to the right. So from 2, the x value is now 6. The other point, 4, is our y value, and that got multiplied by -3 first, and then we added 10 to it. And that gives us -2. And so these are the coordinates of A prime, which is the new location of point A on this quadratic right here. We're going to try and use transformations to actually sketch the entire graph of this equation, y equals -3 times x minus 4 squared plus 10. And if you know your transformations pretty well, you would know that, well, let's start with a basic quadratic. Let's list all of the transformations that actually happened to y equals x squared and see where that graph might end up if we were sketching it one step at a time. I'll invite you to pause the video here for as long as you need, maybe even as long as 10 or 15 minutes, to see if you can figure out where this graph would be just using the idea of transformations and the order that they happen. Well, first let's look at A. A in this case is -3, so there was a vertical stretch by a factor of 3, and of course a reflection in the x-axis. H is 4, so it got shifted 4 units to the right, and K is 10, so it got shifted 10 units up. Dealing with the x values first, if we were to maybe have a table of values for this quadratic, I know that for every single point, the x values increase by 4. That's how we moved 4 units to the right. So to all of these, I'll leave the y coordinates alone for now, and I'll take all of my x values and I will add 4 to them. And if I do that, then each one of these points, which is on my original quadratic, will move 4 units in this direction, right? Their values increased by 4 only along the x-axis. And my new quadratic will be sort of like right over here. Next, I'm going to take a look at the y values. So I've already applied h, excuse me. Now I need to apply a and k. And of course, the first one I'm going to apply is a. So I'm going to take all of my y values, and this is the quadratic y equals x minus 4 squared, right? The only transformation applied was this. So I'm going to take these values, these y values, and I'm going to multiply them all by -3. So what happens when I do that? Well, the x values, of course, will remain the same. And then if I multiply all of them by -3, their distance from the x-axis will increase. What do I mean by that? So let's say this one here is at, so right now it's at 3 and 1. So that's this point right here. Its y-coordinate got multiplied by -3. So if I multiply it by 3, its distance from the x-axis just tripled. It used to be at 1, now it's at 1, 2, 3. And the same thing happened for every single point. This point was at 4, and now it's going to be, well, it's off my graph entirely, but it's going to be at like 12. This point here was at 0, and so it hasn't moved at all, because 0 times -3 is still 0. Now, of course, I only did multiply it by 3 to get this. Remember, if I multiply by -3, all of these will be on the other side of the x-axis, just like that. And so this is my quadratic y equals -3 times x minus 4 all squared. Finally, let's deal with the vertical shift. So all of these coordinates have to move 10 units up. And these are their new locations once I've just changed their y values to be 10 higher than they used to be. And so all of these points will just go like this. And there you have it. That right there is the quadratic y equals -3 times x minus 4 squared plus 10. That's after all the transformations have been applied one step at a time. Now, that takes a really long way, and I wouldn't want you to have to draw 3 quadratics every time you're trying to sketch out a quadratic from vertex form by using those transformations. So of course there are shortcuts to this. So I'm going to start this just one more time. But this time, because the h value affected all the x values and the a and k affected y separately, I'm going to do something interesting. I'm going to start with a first. Okay, so I'm going to take this quadratic and I'm going to multiply all the y values by -3 first. And that gives me these values here, of course. And because, h is affecting the x values, it doesn't really matter that I did these first, as long as I do k after I do a. And so just multiplying these all by -3 sort of creates a quadratic that is vertically stretched by a factor of 3 first, and then flipped upside down just like that. Now what we can try to do is we could try to apply both the h and k values in one step. So that means moving it 4 to the right and 10 straight up. And that right there is my quadratic already done being graphed. So if I apply A first and I recognize that, hey, H and K both are just shifts, and so they don't really interfere with each other in any way, I can just move that boop boop and go right there. And the most interesting thing to notice about this is the vertex, which used to be at 0, by multiplying it by -3, that didn't really change a thing. In fact, only adding or subtracting can change the number 0, right? Multiplying, square rooting, all of those things don't affect it at all. And so the vertex, the fact that it was at 0, 0, it's really, really helpful that now we can find its new location just by looking at h and k. Because those are applied in sort of one step at a time, and they're the only ones that, the only values of the three transformation values that actually affect the vertex. So compared with the graph of y equals x squared, the graph of this, which is a quadratic in vertex form, is also a parabola, but it has been transformed. It's either been stretched or compressed vertically by a factor of a. It's been translated horizontally by h and vertically by k. As well, if this is negative, then of course there has been a vertical reflection or a reflection in the x-axis. The vertex is super, super easy to find, and this is actually why we call this vertex form. All you have to do is look at the h and k values. The vertex is always at those coordinates. And because you can easily pluck out the vertex from those coordinates, you can also pluck out the axis of symmetry. The axis of symmetry has the same x, it's always x equals some number, and that number is always the x coordinate of the vertex. So you can always pull that right out of a quadratic in vertex form super, super easily. And when you're transforming a parabola to sketch a new one, you can follow the order of operations, of course, right? If you have any point, you can take the x value and add h, and you can take the y value and multiply it by a, and then add k. And that will give you the new location of any point on the original one, on the original quadratic. And you can use that to sketch the graph of a quadratic, although there might be an easier way. Now, if you want to go backwards, of course, this is also possible. Because you know exactly where the vertex is, going to be, or if you can find that out, you can always put that in right here. If you know one other point, if you know x and y, you can just solve for the one unknown variable. And in fact, this is sort of true in any equation, right? If you want to try and find either a or h or k, you will need the other two. But as long as you have those two, and if you have one other point, well, this equation only has 5 unknown variables in it, and if you know 2 of these and 2 of these, that's 4 in total. You can always isolate to find the 5th unknown variable. If you know a, h, and k, you have everything you need to put them in right here and create an equation that graph is going to be a parabola that you'd be able to sketch pretty well because you'd know where all of the key points are and you'd know exactly how stretched or compressed it is. In this example, we're going to actually sketch that same parabola here without using any transformations. So in fact, this is where y equals x squared would be, but I don't even really need that. All I need to know is the vertex is at h and k. And so that's going to be at 4 and 10. I'll put that point right over there. That's the vertex. And now all I need is really one other point to draw a parabola. So what I'm going to do is I'm going to choose an x value that's close to the axis of symmetry. So the axis of symmetry is right at x equals 4. So I might choose 5 or I might choose 6. I might choose 3 or I might choose 2. In this case, for no particular reason, I've chosen 6. So if I choose x equals 6 and I plug it into this equation, that will give me the y value, and it turns out that that's -2. So what this means is there is another point on the graph of this parabola right here at 6 and -2. Now remember, I said I wanted to plot this a little bit away from the axis of symmetry, which would be right over here at x equals 4. And because I found a point 2 units to the right of the axis of symmetry, I know that by the definition of symmetry, there is going to be another point 2 units to the left, and I can plot a point right there. And you can confirm that just by taking 2 and plugging it into here, and you will get -2 as well. But I didn't need to actually evaluate that equation because of what I know about symmetry. And because of this, now I can just connect 1, 2, 3 points with a nice smooth curve, and there's my parabola. So this is one way to very quickly sketch the graph of a quadratic relation, a parabola, if it's given to you in vertex form. Just plot the vertex, find the y value of a point that is very close to the axis of symmetry, and then, of course, plot that same point on the other side, the exact same distance away, and connect those points with a smooth curve. In this example, we're going to actually find the equation of this quadratic relation. And in this case, we only have 2 points, the vertex and the y-intercept. But of course, this is the only parabola that these 2 points could possibly, I guess not the only parabola that they would create. I guess one could go down this way. In any case, I guess I'm rambling here. So let's say this is the vertex, this is the y-intercept, and that's all the information we need to come up with its equation. The equation of a parabola in vertex form, of course, is this right here. It has 3 parameters, a, h, and k. And this is a point on the parabola. This is also a point, but this one is very special. We know that this point is just any random old x and y pair, but this one is h and k, because this is the vertex, and the vertex has very specially labeled letters for its coordinates. So what this means is, if I take this equation and I replace all of the variables except a, because I don't know what a is, but I know y is -3. For x that is related to that y, it's 0. For h, it's -2. And for k, it's +1. I can plug that in there, and then I can solve this equation for a. If you'd like to do that yourself, go ahead, pause the video here and see if you can figure out the exact value of a, and then write down the full equation of this parabola, or of this quadratic relation, in its vertex form. Well, hopefully you recognize that. Let's just simplify this and isolate. So 0 minus -2, subtracting a negative means adding. So 0 plus 2 is 2. We have to follow BEDMAS, so before we multiply it by a, we'll do 2 squared to get 4. And now let's start to isolate a little bit. So I'm going to subtract 1. That'll cancel out the +1. And I have to subtract 1 on the other side to get -4. And now I'll divide both sides by 4 to find out that the value of a is equal to -1. And so if I'm taking the quadratic in vertex form, I'm going to replace a, h, and k, and I'm going to leave x and y. And so the equation is y equals -1 times x plus 2 squared plus 1. Notice that this is x plus 2, whereas this is x minus h. Because h is -2, and that's what made this go turn into +2, because this is 0 plus 2. It would be simpler just to write it as x plus 2 in the equation itself, so that we're not having to repeat knowing that whenever we're trying to evaluate for a variable. And so this is the simplified version, and this is the equation of the quadratic relation graphed here in its vertex form. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.